In this machine learning class, we will see the example for Bayesian belief network from third unit, Bayesian concept learning. And in this class, we try to understand the structure of Bayesian belief network and conditional probability table, and an example that there was rain today. And then we need to find the probability of Paul being late to the class and the probability of Tim being late to the class by using the values of conditional probability table. Okay, so this is Bayesian belief network and this is conditional probability table. Okay, the values are given in the conditional probability table. And after that we will see the hard evidence and soft evidence of Bayesian belief network. Bayesian belief network, it is otherwise called as Bayesian network, belief network, decision network or Bayesian model, whatever it may be, this is called as Bayesian belief network, right? Then what is Bayesian belief network? It is a probabilistic graphical model. Probabilistic graphical model is Bayesian belief network. It represents a set of variables or attributes and the conditional dependencies of these variables or attributes by using directed acyclic graph. For example, we are having two variables A and B. Okay, the variables are represented as nodes. Variables are represented by nodes and the conditional dependency, isn't it? So that is dependent by the arc or edge. Okay, now this is directed acyclic graph. Here A is independent variable and B is dependent variable, that is conditionally dependent variable, right? So this arc represents the relationship between A and B. And now let us see some more detail about the Bayesian belief network. Here this is the Bayesian belief network. Here we are having nodes and arc. So this is node and this is arc. Okay, two arcs are there, three nodes are there, and that is used to determine the joint probability of variables. Okay, all the nodes are consisting variables. Okay, so the node represent the discrete or continuous variables. Discrete or continuous variables, that means the variable values will be discrete or continuous, and that is used to calculate the conditional probabilities, right? And next one is arc. So this is arc. Arc is used to represent the relationship of those variables. Okay, that is the causal relationship of variables, right? So nodes and arc combinedly form the Bayesian belief network. Here the arc state that the node variables are conditionally dependent of its parent node, right? For example, we are having two nodes A, B. Okay, these two nodes are connected with one arrow. So this is directly acyclic graph now. Here A is parent node and B is child node. Okay, so the child is dependent on the parent, but parent is independent. Parent is not depending on any other thing, but the child node is depending on the parent node. Okay, so the child is called as descendant of A, that is the parent node. And the next one is conditional probability table. So for each variable, in this diagram we are having three variables: rain today, Paul late to class and Tim late to class. Okay, for all the variables there is a separate conditional probability table. So this is for rain today variable, and this table is for conditionally dependent variable, that is Paul late to class. Paul late to class with respect to rain, and this is the another variable Tim late to class with respect to rain. Okay, so for each variable there is a separate conditional probability table, and we can use this Bayesian probability to calculate different behaviors of variables. So based on this, we can easily identify the relationship between the variables and the probability and the behaviors of the variables also. Let us see the problem now, and this is the Bayesian belief network. So in this network, the root node is rain today. The root node is rain today. This is independent variable, okay, and two dependent variables are there. The first one is Paul late to class and second one is Tim late to class, okay. So these two are dependent variables. These two are dependent on the root node, that is rain today. If rain today, then Paul late to class. If rain today, then Tim late to class. This is what we can understand from this diagram. And now the conditional probability table for this root node, okay, that is rain today. Rain today, that is root node probability. True, rain today is true, the percentage, that is probability value is 0.1. And the false, that is rain today false, means 0.9. Rain today true means today rain will come. Rain today false means no rain for today. Okay, so these are the values. And now the dependent variable probability, conditional probability table for Paul late to class. Okay, Paul late to class based on rain today root node. Okay, so this is Paul late to class and this is rain today. Okay, so note conditional probability. Conditional probability. Paul late to class true and rain today is also true, then the probability value is 0.6. Paul late to class is true and rain today is false is 0.5. Okay, and Paul late to class is false and rain today true is 0.4. Okay, 0.4 how we will get? 1 minus 0.6 is equal to 0.4. And here both are false. Paul late to class is false and rain today is also false is 0.5. How this 0.5 we got? 0.5, that is 1 minus 0.5 which is equal to 0.5, right? So simultaneously the next node, that is Tim late to class, this is also independent, that is dependent variable. Okay, Tim late to class and rain today. So both are true, the probability is 0.8. Tim late to class, rain today is also true. Okay, in that condition the probability is 0.8. And Tim late to class is false and rain today is true, this is 0.2. Okay, that is 1 minus 0.8 which is equal to 0.2. And the next one, Tim late to class is true and rain today is false, the value is 0.1, right? And Tim late to class is false and rain today is also false, the probability is 0.9. Okay, that is 1 minus 0.1 which is equal to 0.9. Okay, so these are the values we got from our problem. Now what we have to do? We have to calculate the different behaviors of the variables. Okay, so we can use the Bayesian probability to calculate the different behaviors of the variable. First one is unconditional probability that Tim is late to class, and second one is the revised probability that there was rain today, and the third one is the revised probability that Paul will be late to the class. So these three calculations we need to do for our problem. So first one is the unconditional probability that Tim is late to class. Okay, what is the probability of Tim is late to class? This is what we need to compute. Okay, which is equal to Tim late to the class based on rain today. Tim is late to the class based on rain today, because Tim late to the class is dependent and rain today is independent variable. Okay, and multiplied by probability of rain today, okay, plus Tim late to the class and no rain today, plus P of no rain today. Okay, so we need to compute both positive side as well as negative side of a root node. Okay, so now we just try to substitute those values from the conditional probability table. Okay, so Tim late to the class and rain today. Tim late to the class and rain today, both are true. The value is 0.8. Okay, this is 0.8. And next one is Tim, that is probability of rain today. What is probability of rain today? Here 0.1, isn't it? This value. Okay, and plus Tim late class no rain today. Tim late class no rain today. Rain is false, but Tim is late to the class. Okay, this value. Okay, 0.1 and no rain today. No rain today value is 0.9. Okay, this value. So the value is 0.17. Okay. From this unconditional probability, the most important use of Bayesian belief network, the use of Bayesian belief network is to find the revised probability on the basis of prior knowledge. So the prior knowledge is already given in the conditional probability table itself, isn't it? So by using this conditional probability table, we can easily find the probability value of the dependent variables. Okay, if we assume that there was rain today, in our example there was rain today, then the probability table, that is the conditional probability table, can quickly provide the information about the probability of Paul being late to the class and the probability of Tim being late to the class. Okay, if today is rain, then what is the probability of Paul being late and Tim being late today? Let us see another scenario. What if we do not know whether there was rain today or not? Okay, and we know Tim is late to the class today. Tim is late to the class today. We know only Tim is late to the class, but we do not know there is rain today or not. Right? So we can arrive at the following probability. Which probability? The revised probability that there was rain today. Okay, revised probability that there was rain today. Because Tim is coming late today, but we don't know whether there was rain or not. So what we have to compute? So we need to compute there was rain today or not. Okay, so probability of rain today based on Tim late to the class. So this is what we need to find, right, which is equal to probability of Tim late with respect to rain today into probability of rain today divided by Tim late. So Tim late, just now we compute, the value is 0.17. Okay, so Tim late, rain today. Tim is late to the class is true, rain today is also true, the value is 0.8. And probability of rain today is true. So probability of rain today is true with the value is 0.1. Okay, and the probability of Tim late is 0.17. So the value is 0.47. That means the probability of rain today as Tim came to the class late is already known, right? Because as per our table value, if the Tim is late to the class and rain is also true is 0.8. Tim is late to the class is false and rain today is also false, then value is 0.9. So from this we can understand Tim is a sincere boy. Until otherwise the rain comes, he will not late to the class. Okay, this is what we can understand here. Similarly, the next one is the revised probability that Paul will be late to the class today. Okay, so what is the probability of Paul late to the class today? Okay, here probability of Paul late with respect to rain today multiplied by probability of rain today plus Paul late to the class with respect to no rain today into probability of no rain today. This is what our formula, isn't it? Now let us try to substitute those values for this formula. So first one is Paul late to the class and rain today. Paul late to the class is true and rain today is true. The value is 0.6 from the conditional probability table. So this is 0.6. And rain today, just now we have computed, rain today value is 0.47. Okay, plus Paul late to the class, no rain today. Paul late to the class and Paul late to the class and rain today is false. This one. Rain today is false. So 0.5 and no rain today. No rain today means rain today value is 0.47 and no rain today 1 minus 0.47. It is 0.53. Right? The value is 0.55. And now let us try to understand what is hard evidence and soft evidence. Hard evidence means instantiation, that is, the hard evidence of node is the state variable is definitely a particular value. Definitely a particular value. Then this is called as hard evidence. As per our example, the hard evidence is Tim is late to the class. Okay. That is, if particular node is instantiated, then it will block propagation of evidence further down to its child node. Okay. So if for example this is A and this is B, if we get the strong evidence value in the B, then there is no need to go further beyond the B node. Okay. So this is called as hard evidence. And when come to soft evidence, the node, that is the Paul is late to the class with prior knowledge that Tim is late to the class. Okay. So Paul is late to the class because previously Tim is also late to the class. So based on Tim is late to the class, we can understand the Paul is also late to the class. So this is soft evidence. So far we have seen the Bayesian belief network and the conditional probability table. After that we have seen one solved example, then the hard evidence and soft evidence of this Bayesian belief network. Right? In the next class we will see the complex scenarios of Bayesian belief network and the applications of Bayesian belief network. Thank you.